So I'm going to build on what we talked about in lab, what we demonstrated in lab yesterday, and hopefully inspire you guys a little bit, show you some examples of some projects that actually use attractors, just kind of get your mind around the idea. I talked about this in lab. These are kind of like cliche, sort of like computational design tropes, but they illustrate a really important point for us in this part of the semester, which is, again, that there's a way to control things parametrically using environmental details, such as like where something is, or like the proximity of it, or like a force from something, okay, or to take some kind of data and use it that's from your model or from the environment, and use that as your parameter, as opposed to you controlling the parameter with your own sliders or with some kind of arbitrary data. All right, and we saw that with the attractor. When you move the attractor point around, it does something to like the parametric form. Hang on a second there. There we go. Right. So these are the examples, right? So we had these 2 points we can move, and they kind of have like a field, right? Almost like a magnetic field or something. And they actually change the radius. And then in this other one, just an example, they make the radiuses sort of grow. And I sort of talked about in the abstract different ways you could use these on like a facade, or as some kind of like a texture, or as like a ground effect. I'm actually going to show you some examples of that today. All right. This is just one way to use computation, but I'm going to show you even just an idea that's as simple as this. Just looking at the proximity of one point to another can be used to all kinds of different expressive ideas. Right. This is a project that's on the books right now. I think it's in Belgrade, and it essentially uses attractors on the facade of the building. There's a particular pattern for this, and what they're doing is looking at like occupiable spaces and non-occupiable spaces. All right. So this is pretty much verbatim like what we just did, only on the scale of a building. All right. And you may not like this, but I'm not sure I like it very much either. But it is an example of this idea at that scale, and they're using it. There's actually these different kinds of patterns that they have. It's not just as simple as kind of making something open or close, but it's actually about choosing from. Let's say that you manufactured a bunch of different panels. They were like 6 different panels. Each one has a different kind of orientation, or like a different kind of opening. And the program actually chooses those based upon this like attractor script. And what you end up with, there are some spaces in the building that they use them as like a canopy. There are some spaces in the building where they use them as like a facade. And it's one of these surfaces that kind of stretches over the building. You can see like a night reversal here. That's kind of more striking than this outside piece. But this is an example. And you could probably use your imagination and already begin to think about how you might do this like parametrically in Grasshopper. I mean, this is essentially a surface, right? So you plug the surface in, get the points on the surface, measure those points according to some attractors. I think in this case the attractors are located, inside of these kinds of spaces. There's a little bit more to it than that, but you could already begin to imagine that. So that's a very basic type of attractor, which is that you have some kind of a module that is parametrically expressive, and in a lot of cases just simply opening and closing something, right? So there's a parameter for these panels, and it's probably just the 2 vertices here and the distance between them, right? That kind of creates that kind of maw, that kind of opening and closing. And when they're completely closed on this side, but they gradually become more open on the other side, and that's because there's an attractor driving this script. The challenge with these, the problem is that a lot of the times, like I talked about this in class, you have something like the sun, and the sun actually moves throughout the day, throughout the year, throughout the seasons, right? This is a fixed thing. Like somebody fabbed this. It's not going to be able to open and close with the sun. It's a fixed amount, all right? You can do it in the computer and make it look like it's animating and it's really cool, but when you actually come to build this kind of a thing, it would take an awful lot of like mechanical pieces that and some kind of like an automation system to actually make it work. And a lot of the times those things don't work, or if they do work, they don't work for very long. All right, that might be changing, but it's something to take into account when you make one of these things with an attractor, particularly when you're doing like solar attractors. It's really difficult to make one that works in a lot of different conditions. It's pretty much just going to be burned. It's going to be fixed, you know. But there, you know, like in this case, there are other reasons why you'd want to create openings in your building. This is another example of this idea. This is a project that actually a student did. Same idea though as the one I was talking about here. There's actually 8 different variations of the cell. There are attractor points along the line in specific like locations, so it's kind of like an even distribution of attractors. And then you can basically map those with various strengths to this form. And what it actually ends up doing is kind of like exposing the kind of like underside of this form. That's where like the purple kind of comes in. So it's not really used as an opening, but as more of an expression of something. So it's like it's sort of like pointing towards something, or it's sort of like influenced by something. And I think there's lights inside of these. You get this purple kind of hue from this. And so again, this is an idea, sort of taking the idea of an opening and making it more about actually taking light and putting light, you know, from these points, as opposed to asking about light coming into the points. All right, this kind of tearing. The form itself may be parametric; it may just be rendered, but obviously there's some kind of surface operation, and that's responding to those attractors. And you could get different operations like this surface. So again, this thing's been tiled, but the variance here is actually that these points. There's probably a curve here with a point in the center, curve here with a point, and the z-coordinate of that point is changing parametrically, and when that curve is redrawn, you get that kind of bulge, or that kind of almost like a fish gill kind of opening up. And we'll talk about these later in like a future class. But basically, you take those curves and that makes a surface. So there's all different ways of basically taking an attractor, looking at the distance, and then basically saying that distance somehow, you know, with a little bit of math, basically like equates to the distance between these 2 points on a surface, or the choice, you know, whether to choose, you know, one of these tiles or the other. There's probably a threshold. So like, let's say the distance is between 0 and 5, it's this tile. If it's like 5 and 10, it's this tile. You can set these up parametrically. There's another example here. This is another one of these that actually it's sort of a combination of this idea with the idea of exposing another material. And it kind of creates this just kind of pretty pattern, I suppose. There's a material behind it. You can kind of see a box in there, and this it kind of gets like unpeeled. So this is another attractor-based piece. There's another one yet again. This one's just about the size of the holes. But so there's an interesting kind of figure ground thing happening though that you can do when you expose something underneath that material. Okay, so this one is just about the size of the openings. There's definitely more space between them here, and less space as it gets into the form here. So let's talk about that a little bit. What we did before was just something with like circles, okay? But it might be interesting to know how you do this pattern with some other forms. All right, so I'm going to show you a little script right now. Okay. Get this going. I am recording this, so don't worry about if you don't catch the flow of what I'm doing. You'll have access to these somewhere else. There's a couple of different things that I'm going to show you with this that are different from what we've seen so far. So first thing I'm going to do is I'm going to take a surface and reference it. Okay, and then I'm going to hide it. And then we'll do our old pattern where we divide domain. Oops. Divide domain squared. So this pattern, right, that we see like all the time, an ISO trim. And that's going to give us some cells. But I'm going to actually increase the number of cells by quite a bit. These only get really interesting when you have a lot to play with. So we'll just grab a couple of these sliders here and get to work. Okay. So these are going to be our cells that respond to our attractor. Okay. Then we need an attractor. And in this case, I'm going to start off with just a point. Actually, I'm going to do a couple of points. Because remember I said in class, like one of the things in the assignment was I gave you a pattern for one attractor, and then I had you guys figure out how to add another attractor, and that was a little bit like convoluted. And I said, okay, there's a way to do it with like any arbitrary number of points. Remember that? That's what I'm going to show you. Okay, and it's actually going to let us do a lot of interesting things. Okay, so I'm going to reference those points. Now I have a point object, and I think you guys have seen this before, but you can pick multiple objects, and then you can right-click something to reference it, and you can say set multiple. So you can say set multiple surfaces, or set multiple curves, or set multiple points. All right. So now there's actually 3 points contained inside of that point object. All right. And this will work with any arbitrary number of points. Okay. So I have this surface, and I have my attractors. Now I'm going to go about basically creating my tractor network. I'm going to get the area. I'm going to get the centroid of each of these. All right. There's just a bunch of surfaces right now. The other thing I'm going to do is the variance is going to be that I'm going to scale these. So I'm going to plug in all the different geometry, plug in their centroids, and so what we're going to do basically is we're going to look at a pattern that's like this. Okay. This is where we're headed. But we got to learn a couple of different things first before we can make that work. Okay, so we got our points. Before, what we did was we had a distance component, right? We looked at the distance between one point and all these other points, and then we did some math to that. I'm going to do something a little bit different. I'm going to do basically like the closest points component, and closest points is really interesting, and there's actually a lot to play with here. But what you do is you basically give it a list of points and a list of other points. And it actually sorts through all those points, and it finds the location of the point that's closest to it, and it returns that distance. So what that actually enables us to do is basically feed it any arbitrary list of these like attractors, and it gets back all the distances. So this lets us actually create these really complicated fields. All right. So the P is the point that you want to search from, and that's actually that's actually all these centroids, and then C is the, actually, I think I always get this backwards. Let's plug this in, actually. Okay. Yeah, so what actually happens is that, so we're going to search this list of points, which is all the centroids for all this, and we are going to search from this, like collection of points, okay? And then what this is going to return for us is the list of points and the distances for all those points. And you see that these are actually structured in some kind of a data structure. We're going to want to flatten that so we get access to those, okay? At least for this. So we have, if we look at these, whoops, did the opposite of what I wanted to do there. Flatten. There we go. Now we get a list of these different values. Okay, I'm going to go ahead and hide this here. Okay, the other thing that we're going to do, though, so we get a list of values, and there's pretty wide range in there. Remember that scale takes a scaling factor, and it's some number, so it's basically like multiplying that. So 0.5 is 50%, 2 would be twice the size, right? So we can't just feed raw distances into this thing and expect to get any kind of meaningful output with that, all right? So I'm going to show you another trick. So we talked about like closest points. That's a new one. The other one I'm going to talk about is called remapping. And this thing is this is really excellent. This component, you feed it a list of values, like any range of numbers, okay, and it returns those remapped to any range of values that you want. So I can plug in numbers from 0 to 1,000, and it can give me back those same numbers remapped to range from 0 to 1, which is really handy, right? Because then if I multiply anything by any other number, I can basically like control that number, and I can make any kind of arbitrary number I want. Well, I'll show you what that means in a second here. So we've got so what this thing takes is it actually takes the values, right? So we plug in the values. It takes a source domain and a target domain. So the source domain, it actually wants what that range of numbers is. So to do that, there's actually a component called bounds. And if you put in a range of numbers, bounds will tell me what what the lower range of that is and what the upper range of that is instantly. It just sorts through all that, finds the maximum, finds the minimum automatically. So that's the bounds, okay? That's the source domain. And then the target domain is automatically defaults here from 0 to 1. Since we're doing scale, though, can we scale anything by 0? It'll break, right? So we're going to just tweak this a bit. I'm going to set the domain manually to 0.1. But check this out. So our numbers came in, and they were arranged from like 0 to 2, and they come out, and the highest that they can possibly be is 1. Okay? Then what we can do is we can plug in that range of numbers for our scale. And I gotta get all these flattened out here. Let's see here. Something's wrong here. Okay. Oh, I see. I only had 9 values. Hang on a minute. This is I always, like I say, I always get these backwards here. If it doesn't work, you do it the opposite way. There we go. If you get a crash, like a hang up like this, if you just press escape, it should actually it should actually pop you out of that. That's what happens when you feed something that's grafted into it. It's really slow. All right. It's getting hung up on the grafted component. Okay. Happens to everybody. Okay. I might have to restart Rhino. Okay. Come on. All right. There we go. Did I stop it? I'm going to open up another copy. Okay. Let's see if that works. Yeah. Whoa. That's scary. Okay. So I've got... That does not seem right. Okay. Yes. Okay. Actually, I'm going to go ahead. I'm going to go open up a file here. Okay. Yes, thank you. Okay. Fortunately, I saved a copy of this before, just because I might have done this accidentally. Okay. So I'm just gonna do this with like a point grid that I've already set up here. So I have like a grid. Okay. So let's assume that's what I was working with, and I put some rectangles on that grid. So it's basically the same thing that I was doing. I just have a bunch of rectangles on there, and I take the all the points that are on that, and I have sorry. Okay. We're going to reference these instead. Bear with me here. Okay. Okay. Yeah, okay. This is working. So let me explain this like script again. Okay, so what I changed in this one, it's the same idea except for I just started with a grid of points, and I use that to put rectangles on it, but it's the same basic idea. From those points, which I flattened, I look at the closest point. So actually, I needed to do closest point, not closest points. That's my problem. Yeah. So just like there's like horizontal frame and horizontal frames, there's closest point and closest points. So you want to do closest point. Okay, so I plug those points in to C, and I plug in the list of points to P, and then I do the same thing where I found the bounds, I plug it in to the map. I'm mapping from point 1 to 1, and then what I did is I added a multiplier, right? Because I said if I have this amount that's from 0 to 1, if I multiply it by some number, I can really easily just say, okay, it's now a range from 0 to 30, or a range from 0 to 10, or whatever. But if I have a range from 0 to 1, it's very easy to add the multiplier. So I plug all those rectangles in for scale, plug in the centroids. So now I have this attractor system that uses any number of points I want. And what I could do is, so I move these points around, and they're going to change it, and then I can go in with my multiplier, and if I don't like that, I can always change the scale of the whole system. So this is kind of like the minimum that was in the other piece that we had. The problem is these don't have any like strength, but they definitely have like an impact on it, and I can go through and I can change the grid to any kind of arbitrary like size I want, and this whole thing's fully parametric. So this will work for any list of points that you have, right? There's actually a if you're not interested in like specific points, there's actually something if you go under vectors, there's a thing called populate 2D, and you can take any curve and you can plug it in, and it'll return just random points inside of that grid. Okay? And so I can take that and I could plug that in here. Let me hide this. And that gives me, the ability basically to just kind of create patterns. So I can go through, and I'm actually going to reduce the number here. So n is the number of points, and s is the seed. So if I have less points, I can change the pattern. Let me increase the scale here. So you almost get like these camouflage kind of patterns from that. So again, any points from anything, you could take a point from a piece of geometry and plug it in. Let's beef these up here. Again, this is actually what's happening. So that's where the points are. These other points are the ones that I referenced. Go ahead and hide those. I know it's a little confusing. Okay, so there's that. So you can do any kind of arbitrary points now and put them into like an attractor field. This actually has interesting repercussions. Okay, so you guys pretty much understand how you could do something like this now, right? I mean, if you construct a grid of something, if it's on a surface, if it's a flat surface, right? By changing the scale of them in response to an attractor, you can develop these kinds of things, right? And the meaning of the attractor is up to you, right? Maybe it's an axis from a view, maybe it's some other kind of metaphorical influence, or maybe it's just arbitrary, okay? But you can create these kinds of patterns. Another thing that we see though are lines that are used as attractors, okay? And those can be useful because they actually would have some kind of like a granularity. You can see how this creates sort of like a grid pattern by actually successively copying that line. There's a bunch of straight lines. I don't know if you guys can make that out from where you are, right? So we can do all these things with points. Does anybody have any idea about how we can do it with lines?
Reference a line.
Well, we reference a line, but then what?
You have to extract the points from them.
You got it. Yeah. Points, you can just basically divide curve on a line that you've referenced, and then just plug those points into the attractor system, and you get these kinds of patterns. So let's give that a shot, okay?
So that right there, where's the curve? Where's the curve that you associated?
There's no curve yet.
In the thing you just did, though?
Oh, in the hang on a
second.
second.
Points that you referenced, and then you changed the curve to a curve. I don't know what the curve is.
The curve that I referenced for like to populate, like 2D is just this box I drew. Yeah, there's no, and that just makes random points. That's not any, that's not any kind of thing. Okay, so I'm going to go ahead and erase some of these here. Okay, so to show you again what we're referencing here, this is the grid. And I'm going to do a big N for Nick. Okay, like Zorro. All right. So reference that curve, and yes, like Savannah said, I'm going to divide that curve, and I need more points though. I think I need more points. So the more points you have, the more you get that kind of influence on that, right? Okay, so if we plug those points into the system, you get the mark of El Zorro. Now, I'm sure you can imagine things you could do with that, though, in your projects, okay? You think about this, too. Like, these don't just have to be flat. You can put these on the surface of something as long as you get the orientation of those things correct. And you could use this on any arbitrary form. Okay? I'm doing it flat because it's easy to show you, right? If you need help figuring this out, I can talk to you about it later. But so that works for any shape, and it's actually parameterized. So if I go in and I reference this curve, I can turn on the control points, and if I move it, it updates. And again, the curve could be parametric. You could do a curve, and you could do like a move in order to create a series of those, right? And then plug those in, get the points from those. That's all it is, right? Get the points from them. And you can create those kinds of patterns. Send it off to the laser cutter, Mackenzie.
Could the bounding box for the grid be like an arbitrary formula?
Oh, totally. That's what I'm saying. Yeah, that grid, this is just anything that you can assign one of these sorts of like parameters to. I'm going to show you in a minute different kinds of attractors. Right now we're just playing with scale, which is kind of like opening and closing something. We can do it with like moving points. We can do it with like rotating points. Anything that you can affect can be affected by an attractor. Okay. Right now it's just like a grid. And that's an arbitrary grid, right? Like play with the size of it. Play with the density of it. Yeah. Okay. So yeah, we have really, really fast updates, really, really, really quick. Okay. You could do any number of curves you want. Just get the points from them. Plug all the points in. Okay. Bob's your uncle. So that's that kind of attractor. I'm going to show you another one real quick. I think I turned off my thing here, but Zorro. Okay. So if I've got, and there's these other components. If you go under grids, we've done a lot with the square grid. There's triangular grids, there's radial grids, there's hexagonal, triangular. This is a triangular grid. So if you want to know how to make those like funky forms, like a starting place is just to go to the grids panel and start to play with those, right? Once you have that, you can take something, and what I'm going to do is just draw a box around it for now. And I'm going to set that for my populate 2D. Hang on a minute. Yeah. So again, this just gives me random points. Okay, that's all that's doing. Same thing. Get the closest points, and then if I go in, I get something like that. So that's actually the example that we saw. Let me go ahead and hide my tri-grid. Right? So that's very close to this. Basically, if you have any like repetitive module, you find the centroid of it, you can scale something to get an opening on it. Nate?
In that one that we saw where it had like the reveals,
Yeah.
Would that just be an additional scale component off of the existing scale component?
Which one with the reveals? Can you tell me which?
Down right.
This one?
Yeah, it's got. That's like the aperture for larger, I guess.
I mean, this is when the scale is very close to 1, so it's almost like the outside of the shell. Or actually, I'm sorry, that's where the scale is 0. So it basically has no like opening. Or I'm sorry, the scale is 1 to 1.
So the extent of the module now is actually the grid.
Yeah, the extent of it is the grid. But any form that you take, you can even draw something in Rhino that's really complex, but it's some kind of a module, and to copy it a bunch of times, reference it. As long as you find the center of it with the area, you can scale it, right, and make an opening out of it. You can do like a jigsaw puzzle that has openings in it if you can make it, right?
How do you do it inversely?
Oh, how do you do it so that it actually grows?
Yeah.
So this is just like the problem that we had in the lab, right? So what you do is you find out what the maximum is, and you subtract something from it. So that when it's the maximum and you subtract from it, it's just nothing. And then otherwise you get the opposite quantity. Yeah, write that down. That's the answer to the lab question. All right? So you guys understand that? So you find what you could do is, we can do it. I mean, if you find like the bounds for it, right? You have a range from 1 to 59, let's hear. You can go in and you can actually say, you could take like domain components. So this is I. This is our domain. This number to that number, minimum, maximum. Plug in a domain component, and you get two outputs. One is the start of the domain, one's the end of the domain. So you just pop those numbers out, right? So Ryan, the maximum number is going to be E. It's 59, right, in this case. I do a subtraction. Plug in that value for A. Take all my values, subtract them from that, and it gives me the opposite. Make sense? You don't invert it. You don't take the math and invert it. You actually just subtract it from the maximum. That's a pattern. That's something that comes up a whole lot. Okay? Good question, though. This is like if you want something to actually grow in response to something, right? That's what you would do.
Nick, how do you even deduct that from a surface? Like, how do you actually turn that into voids on the surface?
Okay, so remember like the porcupine pattern? We keep talking about this when you have a surface that has like a flow on it, right? You can find you can find each of those little mini surfaces on there, and then you scale it according to each of the individual planes that flow, and then you get the same thing. You basically like offset each surface from each other, or offset the edge of each surface, and that creates an opening. We'll actually talk about this in a week. Yeah, that's where we're headed. Yeah, but good. Yeah, it's the same principle though. It's happening in 3 dimensions. Totally possible. Okay, I'm gonna I'm having too much fun. So, all right. Yeah. Okay. So so this is the same pattern we had before. I'm going to set this curve. Do it. Yeah. Oh, and I hit it, so that's why it's not showing up. Okay. And I get my points from it, and my points going here. It's not showing up. Okay. Anyway, well, you could I did the opposite again. Keep doing that. Okay. So it actually goes into C. Yeah. All right. Okay. So you can, as long as you get the points, there's my Z. There's my Zorro. Interesting. Okay. So attractors. Let's keep going. Okay, so we've looked at these patterns here. The other things you can do with it, right, is that, again, if you have, it's just numbers. So when you have a number that refers to something, to the scale of something, it could just as easily be something that says move something in the Z a certain amount, right? Or move something in the X, or move something along a vector. It's just a number. It's an amount. Move it a lot, move it a little, okay? So in this case, we had these attractors that are on a surface, and we're pulling those points, in this case, up in the Z as they get nearer to the point, and in this case, down as they get nearer to this attractor. Okay? See a lot of examples, these kinds of things. Oh, this is Revit. Revit, you can program to use attractors as well. This isn't just a Grasshopper like principle. Okay? As I've tried to explain to you guys, and I don't do a good job of showing you visual examples, this is not an idea that's just Grasshopper, that's just Rhinoceros. You can program this in Revit. It's a little bit harder to do. It takes a little bit of code here, but it's certainly possible. You can do this in digital projects. You can do this in Maya. You can do this in Studio Max. Okay? Probably do it in SketchUp. Somebody's probably got a way to do it. It's just a simple idea. It's just looking at distance and making it parametric. So this is a Revit, and this is actually taking these like panels and extruding them. So they're all flat, but you're extruding the outer edge of it, and that's creating that sort of facade bulge. This is extruding in the, Y, Z? X. X. There's only 3 choices. Extruding in the X. Okay. This is another example. So there's some kind of like a Voronoi kind of thing, and this is extruding it the opposite here. So here it's not being extruded very much. In the back it's being extruded like quite a bit. Okay, and the color is actually changing in response to it as well. Okay, change the position of the piece, and change the form. Okay. There's another example. So we have this thing, and in this case, the attractor is actually like a shape instead of just a point, and it's actually creating this kind of bulge in this field. Here's an example of, so this was done, these points along the surface were like pulled, but they have a very quick fall off. There's not a lot of influence on the attractor, so they fall off quickly. And then someone came through and cut sections of this. So it started off as a surface or a solid with these bulges, and it was like cut. So you don't have to stop with, this. Actually, this one's actually got openings. You look at this one here. See, the openings are actually changing size as well, in addition to the height. Do that. Okay, so let me quick show you an example. And I'm going to use the one that I already made in this case instead of trying to do it on the fly. All right. Take you through my example here. Okay. What I've got is a surface. And I'm just dividing it up, okay? Same pattern as always. Getting the area centers. And I'm doing all the stuff that I was doing before. I'm looking for the closest point. Let's make some points. I'll make 3 points and reference those. Okay, and plug these in. Okay, and what I've done is I've got the bound. Oh, so hang on a minute. Yeah. Okay. So what I'm going to work with here is actually color. And the color comes in as a gradient component if you want to map color to something. Okay? And a gradient component has the lower limit and an upper limit, and then you feed the values in. So it actually says it's a map. So like if you have a list of numbers from, let's say, 0 to 1, right? 0.5 is going to be somewhere between this pink and like that red. So it basically creates a map. Okay, you can, if you right-click on it, there's different presets. So I could just do it as like a black and white. I could do it as like a heat map. I could do it as a rainbow. There's all kinds of different like ways to do this. You can also make your own gradients, just like you do in Photoshop. But these are really useful for like color coding diagrams of things, or even changing the facade of your building to be different colors. So what I've done is, gotta delete this. There we go. What I've done is I've got, just like the pattern I showed you, I have the bounds. I took the upper domain and the lower domain, and that's L0 and L1. Then you plug the values in for T, so the values go straight in. So just like the mapping that we did before, essentially it's mapping it on the gradient. Then what you get out of it is actually a range of colors. These are colors, right? They're RGB values. You can't just throw color on an object. This is where it gets tricky. And I'm going to try to explain it. You can't just throw color on an object. You actually have to convert the surface to a mesh. And the surfaces are these, really smooth, kind of like they're basically made up of, like nerves, right? Which are these smooth curves. A mesh is a bunch of little square or like triangular facets, and that's actually what computers, basically work with. That's what your video games are. Even the nerves actually get turned into meshes before they get drawn on the screen. But you can't just assign the color to the surface. You need to convert it to a bunch of surfaces and then assign the colors to those. All right? Because basically because there's nowhere else for the color to go. It treats it as one surface until you make it into a mesh. So you break it down into a mesh. There's a component called mesh surface. It says mesh UV. I don't know why. It's one of these Rhino things. Mesh surface. You plug in the surface that you started with, which is my grid here. And you need to make sure that the UV is 1 less than whatever this is. So this is 17. You make this 16 because of the way that it uses the points. You should probably make a dependency there, right? You plug in the 17, you do U minus 1, V minus 1. But I was lazy. I just do it manually. You'll see why that won't work in a minute. You take the mesh, and then you drop in a mesh color like component. Mesh goes in one end, color goes in the other, and the two like come together and give you your surface. All right? And again, you can blend these together. And any number of points, guys, that you want, anything. Take a map of the city, right? Draw a point on each building. Or take a path for somebody. Like take a curve, plot the points on the curve. You got a heat map, right? So this is a really great diagrammatic tool for these sorts of things. And it works for any arbitrary. Now, see, the problem is, this is what happens. If I make this 17, right, the data gets really confused. Maybe you'd think that's cool, but it is pretty cool. But it's not right, okay? They got to be balanced. So I could, if I wanted to do the opposite, I could take what Ryan said, right, and I could take the maximum, and I could do a sort of like subtraction. And then red would be hotter where there are points, right? If I just reverse the values, or I could change the gradient values. If you go in, you could change the gradient values by right-clicking on the points here. I can make it whatever I want, so I can make it go to blue or something if I wanted to. Anyway, okay, so you can change the gradient to whatever you want. So again, you can take a surface, and you can take any surface you want, and you turn it into a mesh, and you can apply color to it. And then you bake the color, and then you can render it. Lindsay?
That was what I was saying.
Yeah, the baking part is actually, you need a little component, which I'll put online tonight. You need a special component because in order to get the color to like go to the right, it basically makes a material for every single like mesh, and then it like figures out how to apply them for you. You can't just bake this; it'll just be gray. Okay, you got to use the bake component that I give you. Okay, okay. So there's that, and actually I'm a little ahead of myself because what I wanted to show you, I'm going to take this surface and just plug it in for this thing here. Okay, what I wanted to show you is this. So all that stuff for the color is there, but there's this other thing. What I wanted to show you was extrusion. So I've got this surface, and I've talked about BREP explode or like BREP components before, baiting and panning, but I want to be really explicit about it now. So there's this BREP components. It's boundary representation, which is just any arbitrary like geometry. It has a boundary. You represent the boundary. It's a BREP. BREP components, which is what you search for. You don't search for explode. Gives you all of the faces, all of the edges, and all of the vertices for any object. So it's really powerful. You get all access to all of like the topological levels of that geometry. Okay, there it is. It's everything. I take the faces of that surface. And right when I extrude a face, when I extrude a surface, I get a solid. Right? You guys know that by now? So I extrude it. So I extrude it into Z according to the distance between a point and a point on the surface. And I need to reference my points here. Crunch. So I extrude it according to the distance, and I color it, and I get a diagram. I get a 3D diagram. Like the stock market or something. Again, any number of points, any arbitrary surface. So this is just about extruding things, right? The amount of the distance becomes the Z extrusion. The amount becomes the color on a gradient. Peter Ron would probably shoot you for that. Maybe not. Okay? So you can make your own gradients for things. What's that? It's reasonably parametric. Oof.
Would you smooth it over?
I just changed the amount of the subdivisions.
I mean, like if you were trying to make like a topo of it,
How would you smooth it over?
like instead of having to be like
These boxes?
yeah.
Just take a bunch of points. So instead, what you want to do is move the points on the surface, and then redraw the surface with those new points. Yeah, same idea. Again, we're just moving geometry in space. Anyway, but you can, so there's that. Okay, so movement. So we've got the three transforms, right? We did scale, we did move. Think about this on the facade, right? Nothing says you can't have a vertical and you're moving it in the x, or you're moving it just towards like some other arbitrary point along its vector. Okay. The last one I want to talk about, for this at least, is rotate. Right? You can rotate according to an attractor. So this is actually where we talk about when we talk about daylighting, right? You know how you have like solar panels in those big fields and they follow the sun? Same idea. You sent an attractor up to the sun, right? And they would, rotate. See what that looks like. Because you guys are going to be making solar panel fields or whatever. But, on like the roof of a building, it might be something that you want to attach to like a louver system. That's possible. Okay. Just go through all this again. So I'm just going to reference my surface here. Ooh, I can shut all this off here. Okay, cool. So I have a surface, I subdivide. Oh, I need my points back though. Let's take my points. Or actually, just take a point in this case. Yeah. Oh, actually, I want to reference this one. Yeah, everything is scaled. Okay. Okay. So I've got a field, and what I did was I subdivided it, get the area centroid, distributed some rectangles, and this is really key here. The rectangles have a grain to them. Anything you rotate probably wants to have a grain, because if it's a cube and you rotate it, then it's essentially like you rotated it in any direction. You only have a range of about 45 degrees where you can tell where you've actually rotated it. That's no fun. Okay, you need something that's got a grain to it. Okay? So we take these and we make this rectangle so that they have a grain. They could be anything. They could be lines or something like that, right? Ovals. I take my point, my attractor, and I draw a vector, which is a line, basically, between that point and all the other points. And vectors don't show up, like they don't look like anything, they don't look like lines. So what you can do is there's actually a component called vector display. And what you can do is you can plug in a vector to it, and then you can plug in where you want to see it drawn from. And so you can actually see where the vectors are. This is one of these interesting components. You see the little fringe on the end of it? That means it has no output. Like, that's it. You don't get anything else out of it. You get lines that you can see and nothing else. Okay? You can just, you can turn it off. Let's take those vectors, and I have another component that takes the angle of two vectors, right? Because if the vector doesn't give me an angle, it just gives me a direction. I need it in reference to some other line in order to give me an angle. So I just take x, which is just flat, and all my vectors that are doing all kinds of crazy things, right? And I just measure that angle. Okay? I'm doing some kind of dance there. All right. So I take x as my other vector. You can take any of those units, right? Z, y, x are all just basic vectors, but they're in a certain direction. Take my arbitrary vector and my basic vector, and I get an angle in radians, and then the opposite angle in radians. So you get what's called the reflex angle. Okay. Then I take rotate. You guys know this story now. Take rotate, plug it in for the geometry. The angle, this is actually already in radians, so we don't have to convert it. And the center point for each one, which is the point of rotation for each one. And I get that. Okay? And then you can do the other stuff I've shown you where you get the closest point, you feed it into it, and you can actually get all these things pointing to a line or a series of lines. So rotation. Scale, movement, rotation with attractors. Okay? Again, actually, you don't even have to think of them as attractors. It's just really about proximity or it's about distance. You get a value, and the value goes into something else, and it gives you different output. It gives you color, gives you rotation, it gives you like movement. You can do all kinds of things with that, right? The three transforms are the foundation of all form making. All right, let's take a look through a couple other things here. We'll finish off the day. So rotation. Now you have a sense of this, right? These are boxes, and they're actually being rotated in a space in 3 dimensions. There's another one, right, where these are perpendicular, and they've been rotated to face a point. And I believe the scale changes slightly. Like a bunch of potato chips or something. This one has a lot more attractors in it, but it's basically rotating. It's a surface that gets like fractured, basically, right? It's a bunch of like polygons, and they're allowed to kind of rotate on that axis in 3D. So they have a fixed like axis that they rotate on. They don't like spin like a top. They're like a hinge. Okay. Vector fields. You see these in mathematics a lot. You see these in like wind analysis. So this is essentially a bunch of points with these little things on them, these little bars, and there are multiple attractors, and they have basically they're being attracted in different directions with different areas of influence, and the length of these is dependent upon how much they're being influenced. So here they're being influenced. It's being influenced quite a bit, and in the fringes it's not. It's being pulled towards that point, and they're rotating, and you get these interesting patterns. And if you do them in like a regular kind of order, if these are like distributed in order, distributed in like a symmetrical way, you get these really beautiful like vector fields. But this is essentially what's happening, right? They might actually be pinned on one end, and they're allowed to rotate about that. Instead of rotating about the center, they're rotating about the edge. It's kind of a magnet. You can get it closer up and actually see what's going on here. So they're just different lengths according to the strengths, and they're different locations, and they're rotating freely. Some more examples of them. Some of them get quite chaotic, but they're still kind of interesting. And you can do different things with, and actually this, I'm not sure where this falls under, but this one's, you can get like flows. So if you actually connect these by lines as they go towards a certain point, you get a flow. If you construct these as a 3-dimensional surface, so you actually, the one I showed you like way back, like this one, so the strength is actually pulling it up or pulling it down. And you cut a section of it at regular intervals, and then you flatten it, you get that kind of a diagram. I'll give you a script for that if you want to do that. That's actually not like it's not because it's really people always ask me like how do you get them to join each other? How do you get them to like create circles and these like whorls or things like that? It's actually a 3-dimensional shape, but you're just looking at the plan view of it, and you're looking at sections cut across it. So you're actually getting a topo of that. I think it's pretty cool. Same with this one, just it's a different kind of influence. Okay. More attractors. So there's positive and negative attractors here. And again, these are the kinds of things that show up in these kinds of wind studies. Now you have a sense of this, right? You have the size, you have the rotation, and the color. I'm not saying you can do a wind study in Grasshopper, but now you have a sense of why they look the way they do and like how they get that way. Okay, there's a value for the wind at each of those coordinates, and there's a parametric system drawing those. This is actually a project that uses attractors that's built, that is actually constructed and quite famous. You guys know the firm Marble Fairbanks? You heard of Fairbanks? Okay, so Marble Fairbanks do a lot of digital fabrication work. This is actually Columbia University. This is one of their new student centers. This was done a little while ago, 2005, 2004. But nevertheless, he uses attractors in a actual project. So the project has different components to it. I'm only going to focus on this first one here, this first surface here. They're actually they all have something to do with basically cutting holes in material in a specific way that's actually computational. But I'm going to focus on the acoustic performance in this area, like the main student hall. And that's actually what it ends up like looking like. Okay, so there's the panels, the acoustic panels in the ceiling were derived by taking an acoustic study using attractors and then basically propagating it to a series of custom fabricated acoustic panels. So what they did was they had a simulation of the space, and they used like some sound generators to check the sound levels at like various points. And then this is what actually ended up resulting. So they had these like hot spots where there was too much like reverberation, and they wanted to actually take that and kind of like lower it. So these little like green pieces here, those are the attractors, right? Where the sound concentrates, that's the attractor. This is actually what the study looks like in 2D. So they like would fire a bunch of sound, and it would tend to like reverberate. You can see it actually reverberating. It's almost, this looks like in the video, it looks like sort of like ripples in a pond. And then eventually it stabilizes, and they can look at that, and they can look at the white areas, and those are those bright areas are where the sound tends to like consolidate, and so those become attractors. You find the centroid of those, and they're attractors. And you can see, again, this is the kind of study done in black and white.
But you're saying they had a program that could simulate the sound?
Yeah, they have like an acoustics thing, yeah, and then they could. This is the 2D like graphical representation of it. And then this is actually what they ended up with. So this is the ceiling panel pattern with this projected onto it. This is the thing that we just looked at. Okay, right? So this kind of attractor pool. And what they ended up doing was, so this is what the attractors actually look like. You can see the red points. You guys know how to do this now. And then they went through and they located the edges, so like where the panels had to be cut. And they did another, and they actually let that sort of dampen the size of it along the seam. And then they looked for where the sprinkler heads had to go and the fire heads had to go. And they made those attractors. You can see, though, so it actually starts to dampen this out. Very complicated. There's some pipes that go across there, the red lines. And then they ended up, I actually did this backwards. This is the slide I should have had first. And this is a slide I should have ended up with. Okay, so that's what it actually ends up being. And then and Rhino. And then so they fed this. This was actually, they didn't do this. They did this with Rhino script. They didn't have Grasshopper back in the day. The Wild Frontier of 2004. But they did do it in Rhino script in Rhino because it's very simple, right? The size of it is based on the value. Like, you could do that. Just simple math. They did this in Rhinoceros, and then they sent it to the fabricator. So these are the drawings for the fabricator, and they're labeled. This is out of Rhinoceros, and this is what it looks like. Just a rendering of like the geometry for this project, and then the installation. So the lights, seams, and that's what it looks like in the actual project. Does it work? I don't really know. They had a pretty rigorous process for doing it. I'm pretty skeptical of it, but it's a little bit more interesting than just like kind of like like popcorn panel or like a flat ceiling, and a lot more expensive. This is a pavilion that just went up at Yale pretty recently, and this is also based on an attractor. This is a different kind of project than the last one. This is what it looks like. What it is it's a surface, just a flat surface that they created, and they effectively just drew like iso curves on it, and then they just let that kind of panelize it. But then the interesting thing was they took an attractor point and they projected they moved the points of the geometry along that attractor, and then they distorted it into this wedge. And then they just built the damn thing. I mean, basically, right? There's more to it than that, but that's how the form arises. So again, we have kind of this pure idea of a parametric value basically just being the form, the like acoustic attractor. We have movement along a vector that's based on an attractor. I'm not sure. I think the attractor was like the center of the quad or something that they built it on. It didn't specify in the article, but I'm assuming that there's some reason for it. This is a Michigan project called I think it's called Tea House for Robots. And this is another one where they fabricated this form, and there's sort of there are these attractors in these points, and there's a camera that watches people's faces and it analyzes whether they're smiling, and in response to how wide they smile, it opens up. And there's robots inside. There's 3 robots, and they live inside of this tea house, and they make tea and toast and things. I don't know. But anyway, it's essentially is fabricated as like an attractor system, and in practice, it's essentially like it's like a negative attractor. It's like a repulsor. The thing opens up. All right, you can read about it. What's that?
What's it made of?
Like a plastic kind of fabric. That's what it looks like when they actually fabricated it. So it's basically cut. I can't remember exactly the name of it, but it's like a cut plastic. It's relatively heavy duty. So anyway, it's a Michigan project. So took you on a tour of Attractors today, showed you some examples, hopefully inspired you a bit. This video will be online, and the scripts will be online later. Have a good weekend.